Welcome to the world where CMOS and TTL coexist. These two giants of the digital logic world, Complementary Metal-Oxide-Semiconductor and Transistor-Transistor Logic, are fundamental components in modern electronic systems. From the smallest handheld device to the most complex supercomputers, they play a pivotal role in shaping the digital age. With their distinct characteristics, CMOS and TTL offer unique advantages that make them essential in various applications. CMOS, known for its low power consumption and high noise immunity, excels in battery-operated devices and noise-sensitive environments. On the other hand, TTL, with its high speed and robustness, shines in high-performance systems. However, the true magic happens when these two are integrated in the same system. It's a fascinating challenge, requiring careful consideration of their electrical characteristics to ensure seamless operation. But fear not. Understanding this integration isn't as daunting as it seems, so buckle up as we dive deep into the integration of CMOS and TTL. First up, let's talk about voltage levels. CMOS and TTL devices have different voltage level requirements. CMOS operates with a wider voltage range, typically from ground to VCC. This means it's compatible with both low and high voltage TTL devices. On the other hand, TTL has a stricter voltage level requirement, typically around 0 volts for logic 0 and 5 volts for logic 1. This difference in voltage levels is crucial when integrating CMOS and TTL. It requires careful consideration to ensure proper functionality. If the voltage levels aren't compatible, the devices may not communicate as expected. This could lead to a variety of issues, such as signal degradation or even device failure. So when you're mixing CMOS and TTL, always remember to check the voltage levels. Remember, voltage levels are crucial when integrating CMOS and TTL. Next, we explore fan-out and fan-in. It's all about how many signals a device can handle. Let's start with fan-out. This is the number of inputs a single output can drive without significant degradation of the signal. CMOS devices generally shine here with their higher fan-out capabilities. They're like the popular kid at the party, able to engage with many guests without losing their cool. Now let's flip the script and talk about fan-in. This is the total number of outputs that can be connected to a single input without overloading the source. Here, TTL devices take the spotlight with their higher fan-in capabilities. They're like the attentive listener, able to absorb stories from multiple people at once without missing a beat. Remember, mixing CMOS and TTL devices in a system requires a keen understanding of these capabilities, as each has its strengths and limitations. So, fan-out and fan-in, another key aspect to consider. Now, let's understand voltage level translation. As we mix CMOS and TTL, one of the key considerations is voltage level translation. When connecting a CMOS output to a TTL input, we may need a voltage level translator. This ensures that the TTL device recognizes the signal as a valid logic high. Now, why is this important? Well, because CMOS operates with a wider voltage range, while TTL has stricter voltage level requirements. So the translator acts as a bridge, ensuring that the TTL device correctly interprets the CMOS signal. On the flip side, when we're connecting a TTL output to a CMOS input, the TTL signal might be directly compatible with the CMOS input, but we still need to pay close attention to the voltage levels to ensure everything operates as it should. In essence, voltage level translation is all about making sure the signals between CMOS and TTL devices are correctly understood, ensuring smooth operation. Voltage level translation is a vital step in mixing CMOS and TTL. Pull-up and pull-down resistors sound important, right? Well, they are. Let's dive into why. In the world of electronics, resistors play a crucial role in managing the flow of current. They're like traffic controllers, ensuring signals go where they need to without causing a gridlock. Now, when it comes to CMOS and TTL devices, pull-up and pull-down resistors have their unique roles. For TTL devices, pull-up resistors are often needed on open collector outputs to generate a logic 1. Think of it as giving a little boost to the signal so it can reach its destination. On the other hand, CMOS devices may require either pull-up or pull-down resistors in certain configurations, depending on the specific CMOS family. In essence, these little components help the system maintain stability and reliability. They might not be the stars of the show, but they sure do keep the performance running smoothly. So never underestimate the power of resistors. Time to delve into propagation delay and power supply considerations. When it comes to integrating CMOS and TTL devices, understanding the concept of propagation delay becomes crucial. This refers to the time it takes for a signal to travel from the input to the output of a device. In general, CMOS devices have a lower propagation delay compared to their TTL counterparts. This might sound like a clear win for CMOS, but remember, lower propagation delay can influence the overall speed of your system. So while TTL devices might consume more power, they may actually offer faster switching speeds. Now, let's turn our attention to power supply considerations. Power efficiency is a key factor when designing any electronic system. CMOS devices operate at lower power and are therefore more power efficient compared to TTL devices. However, TTL's higher power consumption is not without its perks. It can contribute to faster switching speeds, which can be a significant advantage in certain applications. But this higher power consumption also means that TTL devices may contribute more towards heat dissipation. Heat management is an essential consideration in electronic design, as excessive heat can lead to device failure. On the other hand, the lower power consumption of CMOS devices makes them less likely to contribute significantly to heat buildup. It's also worth noting that the power supply voltage for CMOS can range from the ground to VCC. This wide range allows compatibility with both low and high voltage TTL devices. TTL, however, has a stricter voltage level requirement, typically around 0 volts for logic 0 and 5 volts for logic 1. In conclusion, when mixing CMOS and TTL, you need to consider both propagation delay and power supply. The ideal choice depends on the specific requirements of your system, including its speed, power efficiency, and heat management needs. Remember, speed and power efficiency are the keys to a successful system. Moving on to noise immunity, buffering, and isolation. When we delve into the realm of noise immunity, we find that CMOS technology generally exhibits superior noise immunity due to its differential nature and wider voltage margins. This means that CMOS devices are less likely to misinterpret electrical noise as a valid logic signal. On the other hand, TTL may be more susceptible to noise, especially in mixed voltage environments. This is because TTL devices have a smaller margin between the voltage levels that represent logic 0 and logic 1, making them more likely to misinterpret noise as a valid signal. Now, let's turn our attention to buffering. In the context of mixing CMOS and TTL, buffering is a technique used to prevent loading effects. You see, when a CMOS output is connected to a TTL input or vice versa, the difference in electrical characteristics between the two can cause degradation of the signal. To prevent this, buffers are employed. These devices act like intermediaries, accepting the output from one device and delivering a suitable input to the other. They help to maintain signal integrity while also reducing the risk of overloading the output device. Last but not least, we come to isolation. In certain situations, it may be desirable to physically separate the CMOS and TTL sections of a circuit. This can be achieved using devices such as optoisolators, which use light to transmit signals between different sections of a circuit. The advantage of this is that it provides a high degree of electrical isolation, reducing the risk of interference and helping to maintain signal integrity. In conclusion, when mixing CMOS and TTL, noise immunity, buffering, and isolation are key considerations. By understanding these concepts and implementing appropriate measures, it's possible to create hybrid circuits that combine the best of both worlds, yielding high performance and robust operation. Noise immunity, buffering, and isolation, the holy trinity of electronics. So, we have covered a lot of ground today. We've delved into the intricacies of integrating CMOS and TTL, exploring the significance of voltage levels, fan out and fan in, and voltage level translation. We've also touched on the role of pull-up and pull-down resistors and how they differ between the two logic families. Furthermore, we've highlighted the importance of propagation delay, power supply considerations, noise immunity, buffering, and isolation in ensuring a seamless integration of these two distinct logic families. We've even ventured into the territories of standard families, mixed voltage devices, input and output characteristics, and temperature considerations. Understanding these factors is not merely beneficial, it's vital. It's the difference between creating a functional electronic system or circuit and creating one that's efficient, reliable, and truly brilliant. And remember, Mixing CMOS and TTL is more than possible. It's an art, an